So in this talk, what I want to discuss is distributed optimization, and specifically distributed optimization with mirror maps. So how can we achieve fast convergence in a setting where we're using mirror descent in a distributed setup? So the setting that we are in is we essentially have this graph with certain nodes, which we say are xi's. And each of these nodes, they have access to some local data or some local objective function, which we call f of I. And all of these nodes communicate with other nodes in the system as determined by the underlying graph structure. So in this particular case, this node xi is also communicating with this node, let's say xj, because there is an edge between I and j. And when we say two nodes are communicating with each other, what we mean is that they are exchanging their parameter values. So they're exchanging this xi and xj with each other. The underlying assumption that we make, which is a bit of a technicality, but we say that the graph is connected, meaning that there is a path from any node in the system to any other node in the system, so that they are indeed connected. So how does this look in if we were to formulate this using formulas? So as I said before, we call all of the nodes in our system. So again, these can be devices, these can be processors, these can be anything that can store a particular amount of data or a particular amount of particular kind of objective function. We have these nodes xi's, and we say we have a total capital N of these computational nodes. And these nodes communicate with each other through this graph structure, where this graph structure is determined by V, which are the nodes in the graph, E, which are the edges, which basically tells us which nodes are indeed exchanging their values, aka communicating. And then we have A, which is the adjacency matrix. And then what we say is that our objective function is to minimize this sum of the fi's at each xi, such that each xi lies additionally in some constraint set curly x. This constraint set can be the whole of Rd, assuming that each x lies in Rd, each xi, sorry. Or it can be a subset of this Rd. So we want to minimize this sum of fi's over all of the i's in our system. And additionally, we have this consensus constraint, so we want each of the xi's to have the same value. So each xi is equal to the other xj's in the system. So in this setup, every particle has access to its own objective function, which is f of I. And the collective goal of the system is to minimize the sum of all of these fi's, plus have all of the particle values, all the node values, agree with each other on the same value. So the one thing I want to note here is that even in a distributed setup, if this curly x is the whole of Rd, we still are in a constrained setup because we have this consensus constraint, the constraint that is constraining us to have equal values for all of the xi's in our system. And again, the goal is to compute this minimizer x star, which minimizes the sum of all of these fi's, such that also the values of all of the xi's are equal to each other. So this is the general setup in distributed optimization. Now, before I continue with the particular setup that we consider, which is a mirror descent distributed optimization, I want to briefly talk about mirror descent itself. So what does mirror descent do and how is it defined? So if we go back to some kind of generic optimization problem, so let's say our generic constraint optimization is of this form. We want to find the minimizer x lying in our constraint set curly x, such that it minimizes this objective function f of x. And again, this curly x can either be the whole of Rd, then we are essentially in an unconstrained setting in this particular case, or it can be a subset of Rd. Now, if we were to solve this constraint optimization problem, with projected gradient descent, our updates would look like this. So what we first do is we have some, assuming that we are in iteration k and we have some value xk, we evolve this xk by going in the direction of the negative gradient, which is what we always do in gradient descent. And this gives us some value zk plus 1. And what we then do is this projection step, so basically this value zk plus 1, we project it back into our constraint set curly x by finding the closest x in our constraint set curly x and the closest x to our zk plus 1 in our constraint set curly x. So essentially 2 steps. The first step is the gradient descent step, and the second step is the projection, which projects us back into our constraint set curly x, where the projection is done using the squared L2 norm. Now, the drawback of this particular method is that for certain constraint sets curly x and for certain objective functions f, projected gradient descent can result in somewhat slow convergence. I won't go into much detail on this here, but for a reference, you can look at example 9.17 in the book by Amir Beck, First Order Methods in Optimization. So, what is then mirror descent? In a way, mirror descent can be viewed as a kind of generalization of projected gradient descent, where this generalization relies on this notion that we will call mirror maps. So, 2 things that we will need in order to define mirror descent. The first thing is the mirror map. This is some function phi, some mirror map function phi, which maps us from our constraint set curly x into the whole of our D. And the second thing that we will need is this notion of the Bregman divergence, which is in a way a kind of distance measure. It measures the distance between x and y using this mirror map phi. So the Bregman divergence is defined as phi of x minus phi of y minus the gradient of phi y transpose x minus y. So having these 2 things, the mirror map and the Bregman divergence, we can define the generalization of projected gradient descent, the mirror descent, as follows. Again, assuming that we have some value xk, the value of x at our kth iteration, what we then do is we apply the function gradient of phi to this xk to give us this gradient phi of xk. This is the thing we then update with our gradient step, giving us some gradient phi of some yk plus 1. So this is just the way we define this particular update step. And then the projection step. So basically the projection step is then done by obtaining yk plus 1 from this gradient of phi of yk plus 1 and mapping this back into our constraint set curly x, now not using the L2 norm but using this Bregman divergence. So essentially we choose the closest point to yk plus 1 in our constraint set curly x, where closest is measured by this Bregman divergence with the mirror map phi. Another way to look at this is if we were to rewrite this step using the definition of the Bregman divergence. What we would then obtain is this second equality. And what this tells us is that basically this algorithm tries to minimize the local linearization of our function f, while not moving too far away from our current point xk. And this idea of too far is measured using this Bregman divergence with the mirror map phi. So just to give a little bit more insight into how we go from this thing into this second equality, basically just applying the definition of the Bregman divergence and then plugging in this definition of gradient of phi of yk plus 1. That is how we would obtain this last equality that I have there. If we were to choose for the mirror map phi the L2 norm. So if phi would be this 1/2 norm of x squared, what we would get is basically our projected gradient descent algorithm that we saw in the previous slide, since basically if we were to choose this mirror map, this gradient of phi of yk plus 1 is just yk plus 1, gradient of phi of xk is just xk, and this Bregmont divergence falls back into the L2 distance between x and yk plus 1. So this is why we say it's a generalization, because for a particular choice of the mirror map, we get back to projected gradient descent. The other thing I again want to note is what I've also said before, but this curly x can either be a subset of RD, or it can be the whole space of RD. Two interesting references for mirror descent is this paper, Mirror Descent and Nonlinear Projected Subgradient Methods for Convex Optimization, and this slide deck, which I think gives some useful insights into mirror descent. Okay, so that was mirror descent in formulas. Let's look at it briefly in pictures. So essentially, mirror descent can be seen as something that moves between a primal space and a dual space using this mirror map phi. So if we just assume that we have some primal space here and some dual space here, starting with our point xk in our primal space, what we then do is we map this into this dual space. This is where this phi, gradient phi of xk lives. So this mapping is done using the gradient of phi. In this dual space is where we update our gradient of phi of xk using the negative gradient. And we get this gradient ik plus 1, which is the way we defined it. This is then mapped back into our primal space to obtain yk plus 1. And then yk plus 1 is mapped back into our constraint set using this Bregmont divergence. So let's say that our constraint set is some subset of the primal space. Then this yk plus 1 is mapped back into our constraint set to get xk plus 1 using this thing over here. Obviously this xk plus 1, I should have drawn it in this curly x. Okay, so again, we're moving between primal space and dual space using the mirror map phi, and the dual space is where we do our update, our gradient update, and then we map back into the primal space. So this is the intuition of mirror descent. Another thing that we can do, and specifically we do this because this is the way we will do the analysis in the rest of this presentation, is we can look at mirror descent in continuous time. So if we define this Legendre-Fenchel convex conjugate of the mirror map to be this thing over here, and the gradient of that to be this minimizer, then essentially we can rewrite mirror descent in continuous time in the following way. So we introduce some variable zt, which is updated using this gradient step. And zt is then transformed back into xt using this gradient of our convex conjugate. Now, the reason that this is the same as the discretized version of this is the same as the mirror descent that I had in the last two slides. If we were to discretize all of this, so if we were to say zt plus 1 is zt minus some learning rate eta being our time step delta t, gradient of f of x t, and then xt being this, the way it is defined here. If we were to plug this definition in here, we would get the arg min of phi of x minus zt minus eta gradient of xt transpose times x. So that is just using this this formula over here. And then this thing can be rewritten using the definition, using the definitions of the Bregman divergence back into essentially this formula that we had over here. So that is showing us that it is discretized. It can be the same formulation. One of the assumptions that is again a bit of a technicality, but I want to mention here, one of the assumptions that we will make is that this gradient of phi star maps directly back into our constraint set curly x. And the reason we make this assumption is that we don't actually have to deal with or worry about the actual projections. We just assume that it is projecting it back directly into our constraint set curly x. If you're interested in these more information on this and also how to generalize it to this actual projection, then this paper on the convergence of gradient-like flows with noisy gradient inputs can be interesting. Now, another way to look at mirror descent, and a way that I find quite interesting, is that we can link mirror descent to preconditioning or to Riemannian gradient descent. There are these two papers which are quite interesting. First one is called Mirrorless Mirror Descent, and the second one is called The Information Geometry of Mirror Descent, which go deeper into this particular setup. But very briefly, the relationship between mirror descent and preconditioning is the following. So if we are to apply Ito's lemma, or in this particular case not Ito's lemma because we don't have any noise, but just differentiating, then what we obtain is this. So the evolution of xt directly. So remember that here we had the evolution in terms of zt. So rewriting the evolution directly in terms of xt, what we get is it is essentially a kind of preconditioned gradient descent, because specifically using this identity, that the second order derivative, the Hessian of this convex conjugate, is equal to this term over here, so the inverse of the second order derivative of the mirror map phi itself, then again using this, we obtain this equation here, which basically says that the evolution of xt is a kind of preconditioned gradient descent. So we precondition this gradient of f using this inverse of the Hessian of our mirror map phi. And I think this is an interesting link, because for me, this idea of primal and dual spaces sometimes is a little bit vague, but preconditioning, I think, has a more direct interpretation. So essentially, we precondition with this Hessian of the mirror map, and that is what is in essence mirror descent. The last thing I want to do is just give a very quick convergence proof of mirror descent, just so we have a little bit more insight into why mirror descent can potentially be useful, specifically why it is more useful than just this projected gradient descent. So if we assume that our objective function f is mu f strongly convex with respect to our mirror map phi, and if we define our Lyapunov function to be this thing here, so it's the Bregman divergence between zt and z star being the dual variable of our optimum x star, and the mirror map here is taken to be this convex conjugate of our original mirror map phi. If we then differentiate this Lyapunov function v, what we get is this term over here. We get this by differentiating and filling in our dynamics for zt. Then, using the strong convexity assumption, we obtain this second inequality. And then, using the fact that this part is less than 0, we obtain this last inequality. Then, if we integrate this dvt, this inequality for this dvt, we obtain this following exponential convergence result, where the convergence speed is governed by this mu of f. So essentially, if we were to compare this convergence speed with the Euclidean setting where this mirror map is chosen to be the L2 norm of our vector x, then the effectiveness of mirror descent compared to projected gradient descent essentially hinges on how large this mu f is compared to mu e, where I've said mu e is such that f is mu e strongly convex with respect to this Euclidean setup, the L2 norm. So this gives us a little bit of intuition into the convergence. All right, so that was the brief introduction into mirror descent, and let's now look into the algorithm that we want to use, which is this distributed form of mirror descent. So the full algorithm for distributed mirror descent, the first one that we're going to look into, is the following. So we basically have, again, capital N agents. We say we initialize these N agents to be Z1 up to Zn at time 0. And then the general dynamics are as follows. So each of our ZTIs, so each of our particles, agents, nodes in our system, whatever you want to call them, has the following dynamics. As usual, it has our gradient step. And in this particular case, because we're in this distributed setup, we assume that each of the Zi's has access to its individual Fi. And then we have this communication part, which is the thing that I mentioned in the beginning. Agents communicate with each other by exchanging their particle values, by their parameter values. And this communication is determined by this matrix Aij. We say that Aij is an n by n doubly stochastic matrix. Again, doubly stochastic is a technicality that we later on use to derive certain convergence results. And it represents essentially the interaction weights. So if Aij for a particular set of ij's is 0, then essentially this Zj, Zi are not directly exchanging values with each other. And if it's any other value than 0, then they are. And then additionally, one thing that we allow for is additive Brownian noise. The reason for this additive Brownian noise is, well, there are various reasons. You would like to include noise either if you're in a non-convex setting to have a more efficient exploration of the objective function space, or your noise can kind of be in the algorithm itself if you only have access to, let's say, a subsample of your data points, or even if your communication structure is corrupted, you can maybe say that there is some additive noise coming from that. And then again, as usual, so exactly the way we had in our mirror descent algorithm, our ZTI is then mapped back into our XTI using this gradient of the convex conjugate of our mirror map phi. Okay, so as I said, Aij represents the interaction weights, and we allow for additional Brownian noise. In the convergence results that I'm going to show, I'm not going to care about this Brownian noise because it makes things a little bit more complicated notation-wise, but it's possible to do it. A thing that will be convenient to work with as well is these dynamics in vector form. So if we define the Laplacian to be L, its vector form can be written as this curly L, this L ID. And then we can rewrite the algorithm in just a convenient vector form in this way. So again, we have our gradient term, we have this curly L applied to multiplying with this ZT. This is our interaction part. And then we have this stacked vector of the Brownian motions, and as usual we make then our projection back into xt using this convex conjugate gradient. Okay, so let's see if we can derive the convergence of this algorithm. So it's attempt 1. Attempt 1 may already tell you that we won't be able to derive the convergence as we would like to, but let's try. So let's try to generalize the convergence analysis that we had for the regular mirror descent in the previous part of the talk. Generalizing to the fact that we now have distributed optimization. So for our Lyapunov function, let's take the sum of all of these individual Bregman divergences between zti and our optimum in a dual space z star. Again, doing the standard thing that we did before, which is differentiating, or if we are allowing for noise, then it's applying Ito's lemma. Then we are left with this, these dynamics for the time derivative of Vt. So we have this term coming from the gradient part of the dynamics, and we have this term coming from the interactions. And now the question is, how can we bound this? What can we essentially do with it? So for the second part, so for this term over here, we can use this triangle equality of that the Bregman divergence satisfies. So specifically in our notation, it would say that xti minus x star transpose times ztj minus zti. Important here is that, again, these xt and zt's, they're kind of this primal dual variants of each other, mapped to each other with the mirror map. So this zt is phi of xt. What we can do is, well, first of all, just rewrite the ordering, then rewrite it through this definition that we have. This should be a star of the way we map between xt and zt. That's this part over here. And then essentially we can also show that this is equal to these three terms of the Bregman divergence. So this term between measuring the distance between ztj, zti, another term zti and z star, and another term zj and z star. Now, what this Bregman triangle equality gives us is that if we then take this double summation over I and over j of the thing over here, then we essentially are left with just this first term. And by non-negativity of the Bregman divergence, this guy is smaller than 0. So our first bound is to then obtain that the dynamics of Vt are governed as follows. So we're just left with this term coming from the gradient. Now, ideally, what we would now want to do is exactly what we did for the centralized setting. So for the setting where we just had one node, we would like to bound this using some assumption that f is I don't know, convex or strongly convex. And then, as usual, as we did before, bound this by the negative minus some constant c times Vt dt, so that we can, by integrating, obtain exponential convergence with convergence rate c. Or at the very least, we would like to say that this is smaller than 0, so that we can at least show some convergence. If the Lyapunov function is decreasing, we can show indeed convergence to x star. But now, what is the issue? So if we were to say, let's say this f is just convex, then we could bound this by the sum of fx star minus fxi. Sum is over y is 1 to n. But in general, the problem is that each x star does not necessarily optimize each fi. So we cannot use the standard bound that we would like to use, namely that this thing is smaller than 0. Specifically, there's also this paper, Network Synchronization with Convexity, that shows that in the case that this x star is not such that it minimizes each of the individual fi's, then the algorithm actually won't converge exactly to the optimum x star. So just to stress this, our x star is such that it optimizes the sum of the fi's, but this doesn't necessarily mean that it optimizes each of the fi's individually. So what can we then do in order to still obtain convergence? Well, one thing that we could do is we could use vanishing learning rates. Basically what we want is we want to get rid of this, this gradient term, and assuming that we have some additional learning rate here, assuming that this vanishes as time goes on, the learning rate decreases, you can actually show convergence. So for example, these papers, dual averaging for distributed optimization, decentralized online optimization with global objectives and local communication, and this distributed online optimization in dynamic environments using mere descent. This is just a subset of interesting papers, but they show indeed this convergence with this vanishing learning rate. Now, what is the issue here? Well, the issue is that assuming vanishing learning rates is could be sub-ideal, since it leads to slower convergence rates. So the closer we get to the optimum, the slower the convergence is going to be, because our learning rate is decreasing. All right, so let's go on with defining dynamics, which hopefully will allow us to obtain exact convergence. And the underlying idea of what we want to do with the dynamics is basically what we had here is we were left with this gradient term with which we didn't really know what to do, how to bound it. So very, very, very intuitively, the idea is to introduce this another term, and this term is this Laplacian times, the vectorized Laplacian times this term lambda. And the idea of this term is that it will somehow compensate for our gradient term, so that because we now have this gradient term and this additional Laplacian times lambda, we will be able to achieve exponential, or let's say exact and exponential convergence. So that is very high level the idea. And the way we can derive this algorithm that I have here is through this notion of the augmented Lagrangian. So the augmented Lagrangian for our problem is given by, we denote it by L, and it's given by f of x plus the product between Lx and lambda, and this L2 norm of the Laplacian times 1/2 times x, L2 norm squared. Now, how do we go from this augmented Lagrangian to the dynamics that we have here? The augmented Lagrangian method proceeds by a descent step in the primal variables and an ascent step in the dual variables. And specifically in our case, if we define this ascent-descent step with the Bregman divergence, then we would be able to get these exact distributed mirror descent dynamics. So they are given by the evolution of zt is pretty much what we have seen before, except, as I said, we have this additional lambda term in our dynamics. And the dynamics of lambda itself are governed by this Laplacian times x. So very high level, you get these things by, in a way, differentiating this augmented Lagrangian and accounting for this Bregman divergence that we will additionally need in this primal and dual, in this ascent and descent steps are. So this is what we then call the exact algorithm. And our hope is that this will be able to converge fast to the exact optimum. So let's try again. What we want is again to define some kind of Lyapunov function, which will then allow us to conclude convergence. And in this case, the Lyapunov function is a little bit more complicated than we had before. Our Lyapunov function v is this c times v1, c plus c times v2 plus v3. Our v1 is defined in a way similar to what we had before. Well, before I actually had it written in terms of phi star and zi z star, but this is the same as just d phi x star xi by properties of the Bregman divergence in the mirror map. So that is our first term. We have seen this before. Then we have a second term which measures the distance between lambda and lambda star. And then we have a third term which is a bit more complicated in the sense that it has this Bregman divergence with mirror map F of x and x star, this product between x minus x star and the Laplacian lambda minus lambda star, and this L2 term of L to the power of 1/2 and x. Again, for the rest of this proof, I will just consider sigma is equal to 0 because otherwise you have all these additional terms coming from the noise. But it's fairly easy, just computationally, just notationally involved to generalize. You just apply e to s lemma whenever I differentiate. Well, the first thing that we need for the Lyapunov function is that it's non-zero. And this holds for a certain value of c. So c is this thing governing, multiplying our v1 and v2. And we can show that the Lyapunov function for a large enough c is non-zero. Okay, so this is the way we define our Lyapunov function. It's the sum of v1, v2, and v3. Let us first start with obtaining the dynamics of the gradient of v1 and the gradient of v2, the time derivative, sorry. For v1, we will do something similar as what we did before, except that now we will work with our evolution in the primal space. So remember when we talked about this preconditioning, we said that by using the fact that xi is this gradient of phi star of zi, we could derive this xti dynamics to be this preconditioned zti dynamics. And then remember, just for the sake of completion, the dynamics of the zti. So we have again our gradient step for our fi, our interaction with the x's, and because we have this exact algorithm, we additionally have this interaction in the lambda terms. So just to remind you, that's this this triangle thing here. Then we will need two properties in order to derive the dVt1. The first thing is this one over here, which is basically just the gradient of the Bregman divergence, where the gradient is taken with respect to the second variable, so it's taken here with respect to this xi. What this gives us is it gives us this gradient, this Hessian of the mirror map evaluated at xi, plus this difference between xi and x star. And the other thing we will need is this fact that the Hessian of our conjugate mirror map multiplied by the Hessian of our original mirror map is the identity. So using these two things and using the definition of Vt1, which was this Bregman divergence x star xi. Did I write that correctly? Yes. Differentiating, we obtain this. So basically this comes from taking the derivative. This also comes from taking the derivative. And this is then just the dxti dynamics. And the interesting thing here is that because our dxti dynamics have this Hessian of our convex conjugate of the mirror map, and because from the derivative of the Bregman divergence in the second variable we get this Hessian of the original mirror map, these things essentially cancel out using this second property over here. So what we're left with, just filling in for the dynamics of xti, is we have this first part coming from the gradient, second part coming from our interaction in x and the interaction in lambda. And one thing that I've used here is that L applied to x star is 0. We can rewrite this in this way, and this is again an interesting part, because remember that initially we didn't really know what to do with this gradient term. But now, because we have additionally introduced this lambda term, we can actually do something with this gradient term. And specifically, if we use the optimality conditions of this problem, we get that lambda star is equal to minus fx star. So by subtracting lambda star here, we also can add an additional gradient of fx star there. And that helps us mitigate this issue of what to do with the gradient term, because this term is actually going to be smaller than 0, even without this assumption that x star minimizes each of the fi's individually. Okay, so doing the same thing for v2, so just taking the gradient of our v2, which was this L2 distance between lambda and lambda star, and using the dynamics of lambda, what we get is this. Now, summing dv1 and dv2 together, this guy will cancel with this guy, and then we are essentially left with this term over here, so this term coming from the interaction in x. We will additionally use this result that we have here, which is this xt Laplacian x is greater than some constant times this L2 norm of Lx. And this kappa beta n is, just imagine it to be some constant, something similar to a Rayleigh quotient. So what we then get is that the sum of this dv1 and dv2 is bounded by this thing that we have here. So it's this L2 norm of L xt minus x star. Again, I have used here implicitly that this thing is 0. And the multiplication in front is this 1 over kappa beta n, which is some constant. Okay, so that is the derivation for v1 and v2, and now we will need to do the same thing for v3, and we hope that taking it all together we will be able to obtain convergence. So in order to do this same thing for v3, we will need one more result, and it is this result here. When I write this norm of some phi, gradient of phi, let's say this is x, basically what we mean is this. So you can prove this result using certain assumptions on your mirror map phi, on your mirror map phi and on your interaction governed by your Laplacian. But I just present it here as a result, and this result basically says that this this term over here, so this norm with this gradient of the convex conjugate of gradient of f plus interaction in L plus interaction in x, is larger than this thing. So this, again, this constant 2 kappa g, where kappa g is some generalized Rayleigh quotient. Again, just imagine it to be some kind of constant. And this mu hat, where this mu hat is defined as the minimum between mu phi and 2. And mu phi is the strong convexity of our mirror map, strong convexity constant of our mirror map. So this is one of the bounds that we will need to bound v3. Okay, remember the definition of the augmented Lagrangian, which is given by this, and observe that the gradient of this augmented Lagrangian with respect to x is given by this second line. Now, what we will do is we will differentiate dv3 in the same way that we've done before. And the interesting thing here is that by the way we have defined v3, its time derivative actually results in this gradient of our augmented Lagrangian. So this is kind of the motivation for the way we've defined v3. It has a relationship to this augmented Lagrangian, which is the thing that we use to define our algorithm. So basically, differentiating, we can rewrite that dvt3 is equal to this product between the gradient of x of our augmented Lagrangian and our dynamics dxt. which if we then fill in the dynamics for xt, again the dynamics of the dynamics in primal space, so in our primal variable xt, you can quite easily, or with some effort, show that it's equal to this. So again, this norm with this convex conjugate Hessian of the gradient of the augmented Lagrangian, and the reason that there is this norm here is exactly from the dynamics of xt, which was with this additional Hessian of the convex conjugate. So that's why we have this term there, plus some L2 norm of the interaction in X. Now, using this result that I didn't prove, but which we just trust holds on this bound, we can essentially bound this dvt3 in this following way. So we have three terms here. We have this, this negative constant that comes from this thing. We have this sum over our Bregman divergence between Zi and Zx, sorry, Z star. This L2 norm of our lambda and lambda star, and this L2 norm of our interaction, so Laplacian times X. Okay. Now we want to take it all together. So remember that V was C times lambda 1, C times lambda 2 plus V3. And remember that we had this bound that we just derived on the previous page for dvt3. And remember that we had already derived that dvt1 plus dvt2 was smaller than this. Adding this all up together, we are left with this bound on our vt. And one thing to mention here is that from our dvt1, dvt2, we get a negative term. And from our dvt3, we get a positive term here. So if we assume that C is large enough so that this negative term wins it from the positive term, then we have this negative term over here. And this is crucial if we want to, again, bound this, these dynamics of the Lyapunov function with something negative. Okay. We're almost there. So then the last thing that we will need is we want to, as usual, bound our dvt by something negative constant vt dt, because then we can integrate and obtain our exponential convergence within the exponent, this constant k. So to do this, we need to first obtain a lower bound on vt. Remember that we had this lambda hat being the minimum of lambda phi and 2. Then we can show that this lower bound, this is the upper bound on vt holds. So some constant, not going into too much detail of what all the terms in this constant are, but C is just our term C that we had before. This has to do with our Laplacian, is the largest eigenvalue of our interaction matrix. This is some constant unspecified, and this is this lambda star that we just defined over here. So this V is bounded by sum over the Bregman divergence plus this L2 norm between lambda and lambda star. You can already see the similarities between this bound that we have on V and this bound that we have on Vt. And essentially the idea is to combine these two to say that dVt is bounded by some constant, some constant times Vt itself. So if we do that, we obtain this term here. So again, essentially just filling into the dynamics of dVt, this upper bound that we have obtained here. And then this is the convergence constant that we obtain. So if we are again integrating, then this is the result. And here I have this M term comes from the noise terms, which we didn't use in the proof, but which are there if you want to do the full convergence. But essentially we obtain exponential convergence, and the exponential convergence rate is governed by this R here, which depends on a few things. It depends on the properties of our mirror map through this phi star. It depends on the properties of our interaction matrix through this kappa n, and on both the objective function and the interaction through this kappa g. So yeah, the good thing is we have succeeded to show exponential convergence with this convergence speed r. Let's look at one numerical example to show that it is actually true what I was saying, which is that the regular interacting stochastic mirror descent is not able to converge because we're left with this gradient term with which we don't really know how to bound it. But then using exact interacting stochastic mirror descent, where we additionally introduce this lambda term with the idea of kind of cancelling the effect of the gradient at optimality, we are able to achieve fast exponential convergence. And we are able to converge much closer to the optimum because we don't have this term coming from the gradient to deal with. So what I do here is I compare interacting stochastic mirror descent with the exact algorithm, so the one coming from the augmented Lagrangian, for different interaction strengths. Interaction strength is basically some epsilon times our interaction matrix, so it governs how much the algorithm focuses on minimizing the term coming from interactions as opposed to the gradient term. And the objective function is a one-layer neural network with 30 nodes. On the left, we have the train loss, and on the right, we have the test loss. So basically just look at the pink line, because the pink line is our our exact interacting stochastic mirror descent algorithm with a high interaction strength. So this epsilon is equal to 5. And what we see is that it converges way lower and way faster from this first part than the other algorithms, which is exactly what we wanted to obtain. Now, the very, very last thing is that we can also extend this into even more interesting settings. So a potential limitation of our interacting stochastic mirror descent algorithm in the way that we have now defined it is that the idea is that the mirror map phi only captures the geometry of our curly x. But what I said before is that if our x is, even if our curly x is the whole of Rd, our optimization problem is still constrained because we want all of our x's to lie in our consensus manifold. Let's say it's some curly x C. So what we can try to do is one can think to incorporate information from this consensus constraint through a second mirror map that acts on this Lagrangian dual variable, so on this variable lambda that we had introduced before. So the idea of mirror descent in general is to adapt to choose the mirror map in such a way that you can adapt to your constraint set and thus obtain faster convergence. So the idea of this additional mirror map is to adapt to the geometry of the consensus constraint. So if we were to look at this in the picture that we drew before as well, this is our primal space. This is the dual space. We now work with two variables, x and lambda, and we map both of them into our dual space. So using this gradient of phi that we have seen before, but now in addition also this gradient of psi, we map them into the dual space. In the dual space, we take our gradient step to obtain this zt plus delta, lambda t plus delta, mu t plus delta. And then we map these back into our primal space. So again, we now work with two mirror maps, one mirror map adapting to our original problem, and the other one, psi, the mirror map psi, adapting to the geometry of our constraint set, so our consensus manifolds, because we're in this distributed setting. Okay, so if we were to look at this in terms of the equations, we would keep the evolution of zt exactly the same as we had before: gradient term, interaction term in x, and interaction term in lambda, and potentially noise. But we would additionally introduce these dynamics d mu t. So before we just had d lambda t is lambda xt dt, but now we introduce this variable mu, which is our mirror map applied to applied to our lambda variable. So if we were to rewrite these dynamics from U in terms of the dynamics for lambda, we would actually get this. So just again to get back to this idea of preconditioning, by introducing this second mirror map which acts on our Lagrangian dual variables, we are essentially preconditioning the dynamics of our lambda. And the preconditioning is done using this mirror map, the inverse of the Hessian of the mirror map psi. So the idea of doing this is that it would result in additional flexibility in the convergence analysis. Okay, so this is the end of what I wanted to talk about. Essentially, we started with just introducing mirror descent, explaining what the benefits of mirror descent could be in terms of the convergence speed. We linked mirror descent to preconditioning with the Hessian of the mirror map. Then we tried to define a distributed mirror descent algorithm. Our first attempt failed because we couldn't show full convergence because we were stuck with this additional gradient term with which we didn't know what to do. So we introduced the exact algorithm, which was based on the augmented Lagrangian which had an additional dynamics in the augmented Lagrangian dual variable lambda, with which we were able to obtain exponential convergence and exact convergence to the optimum, since lambda essentially mitigated the effects of the gradient. And then the other extension that we briefly talked about is to even introduce a second mirror map which would adapt not to the original problem but to the consensus manifold constraint to obtain even more flexibility in your convergence analysis. Okay, so what we have shown is this computational efficiency. We have shown that our exact algorithm can reach the optimum fast, and we can converge close to the optimum. Other things that you could look into is the robustness of the algorithm. So what happens if the underlying data distribution changes, or what are exactly these effects of the noise? And the interesting thing is also to look more into what are the right mirror maps for this extension that I introduced. So how can we choose the mirror map in such a way that it is able to adapt to the consensus manifold constraint? That's the end for this presentation. Thank you for listening.